In this lecture today, I'm going to introduce the sediment transport module in EMS briefly. And this is this is the diagram to show how sediment transport module works in EEMS. So sediment transport model is strongly coupled with the hydrodynamic model simulation. For example, at a single time step, we will hydrodynamic module will compute the flow field in the model grid, and based on that flow field, sediment transport model will compute the sediment transport behaviors in water columns and sediment bed. So, and it also computes the interaction between the water column and sediment bed. For example, the flow when the flow water flows with large force. When the flow has a large force, the sediment materials in the riverbed will be eroded and transported into the water column, which is called erosion. And when the flow has a small force, the sediment materials in water column will be settled onto the sediment bed, which is called deposition. And as the sediment bed properties are changed, we can expect the bottom elevation of the model grid will be changed. So such morphological changes are included, will affect the hydrodynamic step simulation at the next time step. So this circulation will be processed while during the simulation of sediment transport model. In EMS, there are two types of sediment transport module are available. One is the original EFDC sediment transport module, which is developed by John Hamnick with Tetra Tech company. And second one is the SED0J sediment transport module, which is developed by Ziegler, Lick, and Jones. Today, we are going to cover the most popular one, which is the original EFD sediment transport module, because, the difference between these two modules is in how we specify the erosion rate of sediment bed. In original EFDC module, the modeler can assign the erosion rate of sediment bed as a user-defined parameter values. And that parameter values will be applied to the entire model domain with the constant value. However, in the SED0J sediment transport module, modeler can specify the horizontally and vertically varied erosion rate of the sediment bed. To assign that spatially varying erosion rate value, the modeler need to have the measured erosion rate values from the field. But such erosion rate measurement technique is only used in the US and used for some specific project. We're going to cover the original EFDC module today. So I'm going to present the conceptual framework of original EFDC approach and shows the transport algorithm for cohesive sediment and non-cohesive sediment, and also going to present how this approach compute the process in the sediment bed. So this is the conceptual framework image of the original EFDC sediment transport module. So the elements recorded in this figure, in this image, are all simulated in EMS original EFDC transport module. So when the water flows in a river, the flow has a flow velocity like this, and that velocity will have a force. The moving water has a force to move, carry the sediment particles. So the vertical distribution of sediment concentration will form like this. And the moving water, the force of the moving water has a large magnitude. The particles in the sediment bed will be eroded and transported to the water column. And the eroded materials will be transported as a bed load and the suspended load. And when erosion happens, the small particles tend to be removed from the sediment bed, but the larger particles tend to stay at the bed. Then the surface of the sediment bed is getting armored, so we call it this armoring process. And there are lots of small particles are transported through the water column in suspension status. And due to the gravity, those sediment particles are settling and deposited onto the sediment bed when the force of the moving water decreases. And after the sediments are deposited into, when the sediment materials are deposited into the sediment bed, the pressure on the sediment bed would increase, so the volume of sediment bed will decrease, which this process is called as consolidation, and the original EFDC sediment transport module can compute all of this process within a single simulation. And here are specific major keys of this transport module, sediment transport module. First one, it uses the linked simulation for sediment transport in water column and sediment bed layers, which means it calculates the sediment transport in the water column and the properties changes in the sediment bed, and it also calculates the flux exchanges between the water column and the sediment bed layer. And modeler can apply the multiple sediment classes with different representative particle size for the simulation. And this sediment transport model separately compute the behavior of cohesive sediment and non-cohesive sediment. And the most important thing is erosion and deposition processes are determined based on the relationship between bottom shear stress and the critical shear stress of the sediment bed. So the bottom shear stress means the force of moving water against the bed. And the critical shear stress means the force that is required to mobilize the sediment in the sediment bed. So as I said here, it simulates the sediment transport in water column and sediment bed layers. The model contains these kinds of different type of layers for water column and the sediment bed. In water column layers, movements of sediments in water column are simulated, and in sediment bed layers are used to simulate the changes in sediment bed properties. As you can see here, the layer order is from bottom to top. Layer order number is assigned from bottom to top for sediment bed layers, and also in the water column layers, set bottom to top numbering. This is the governing equation for suspended sediment transport in water column, and this equation is same as the previous governing equation used in the temperature or dye transport in yesterday lecture. But here the C value is represent the concentration of each sediment class. And we have here the vertical boundary conditions that specify the flux between the water column and the bed surface, and the water column and the air area. So for example, at the water surface, there's no flux between water and there's no sediment flux between water and air. So the vertical flux is 0. And at the bed surface, where is the bottom of the water column, there's an erosion and deposition processes. So this JO term represents the net sediment exchange flux between water column and bed. And the more mathematical details are written in EFDC plus theory document, and you can download this document from our EEMS website. And what is the difference between cohesive sediment and non-cohesive sediment? Those two categories are specified by cohesiveness of each particle material, but usually we distinguish those two categories based on their particle sizes. For example, cohesive sediments are comprised primarily of clay-sized particles and silt-sized particles, which are smaller than 62 micrometer. And the non-cohesive sediments are primarily the sand-sized materials and the gravel-sized materials, which are larger than 62 micrometer. So let's see how EFDC sediment transport module simulate the behavior of cohesive sediments. So cohesive sediments in bed layers can be eroded when bottom shear stress tau B is larger than the critical shear stress for erosion of cohesive sediments. So tau CE is a user-specified parameter, so you can put any number you want during the model development. And also the amount of the erosion sediments is determined by a reference surface erosion rate parameter. So as I said before, you can put any number for the surface reference surface erosion rate parameter values. And the eroded cohesive sediments are transported as a suspended load in water column layers. So the concentration of cohesive sediments in water column layer can vary in space and time, and it can be computed based on the flow field, based on the hydrodynamic simulation result, and the sediment load coming from upstream river, and the sediment flux between water column and sediment bed. So for example, if the sediments are eroded from the sediment bed and transport into the water column, the concentration of sediments in the water column will increase. And if the particles are settled and deposited into the sediment bed, the concentration will decrease. Then how we can specify the settling velocity of the cohesive sediment in suspension? We can put any user-defined constant number, or you can choose several available options to calculate the concentration profile as a function of the settling velocity values as a function of concentration profile and shear stress and the turbulent intensity of hydrodynamic flow field. And then the deposition of sediments occurs when bottom shear stress tau B is smaller than the critical shear stress for deposition of cohesive sediment, tau CD. This tau CD value is also user-specified parameter, and the deposition of flux can be calculated as a function of settling velocity and the near-bed depositing sediment concentration here, and the probability of deposition PD, which can be calculated based on the relationship between the critical shear stress for deposition value and the flow bottom shear stress. Now we'll see how the model simulate the non-cohesive sediment behavior. Erosion of non-cohesive sediments occurs when bottom shear stress tau B exceeds the critical shear stress tau CS. For the cohesive sediments, we put its critical shear stress as a model parameter, but for the non-cohesive sediments, we can calculate this critical shear stress value based on some reference diagram. To compute the critical shear stress for non-cohesive sediment, we can use the shears diagram that describe the dimensionless critical shear stress tau CS star as a function of dimensionless particle size d star. So in this diagram, the black bold line represents the value of critical shear stress of each particle as a function of dimensionless particle size. So the y-axis represents the dimensionless shear stress. So if the dimensionless bottom shear of flow is larger than this line, the particles in motion, so erosion occurs. And if the flow shear stress is smaller than this line value, there's no particle motion, so the particles can be deposited on the sediment bed. The eroded non-cohesive sediments can be transported as two different types. One is suspended load, and the other one is bed load. The classification of suspended load and bed load can be determined by the shear velocity, which is the square root of flow shear stress tau B, and we can call it U star. The suspended load occurs when the shear velocity U star is larger than settling velocity of that particle, and the bed load occurs when shear stress value is smaller than the settling velocity of that particle. So the suspended load means the particles are uplifted by flow and maintained in suspension by while they are traveling by flow turbulence. And the bed load means the rolling or sliding along the bottom of the bed. So how the model to simulate the behavior of suspended load in here. So near bed, the concentration of suspended load of non-cohesive sediment is determined by the near bed equilibrium concentration CE, and it can be calculated based on this equation, and we can choose one of these during the model development. And the settling velocity of the suspended load particles can be calculated as a function of sediment particle density and the effective grain diameter and the fluid kinematic viscosity. For the bed load, we can use the multiple function to compute the bed load transport rate, QB. And usually we use the Van Ryn's equation, but the 4 other equations are also available to calculate the sediment load rate moving as a type of bed load, which is rolling and sliding along the bottom of the sediment bed. So far we've seen how the cohesive sediments and non-cohesive sediments are transported in the water column. Now we are see how the sediment bed properties are changed during the simulation. In the model, this image shows the composition of sediment bed layers in the EFDC sediment transport model. So each of the multiple bed layers contains mixed sediment class materials. Let's assume we decide to use two different classes for cohesive sediment, and use 3 classes for non-cohesive sediment. And these percentages represent the fraction of materials of each class within this bed layer. And the fraction of bed layers, fraction of each material in each bed layer can vary in space, in vertical direction and in horizontal direction. So we can see there are different fraction distribution of the sediment materials. However, so what is the role of these sediment beds? The top 2 layers are used for computing mass exchange between water column and sediment bed, and it also used for computing the mass exchange between the top layers and the lower layers. At the beginning of the simulation, the top 2 layers will have 0 thickness with no materials. And the lower layers are used to represent the physical properties of the sediment bed at the beginning of a simulation. And during the simulation, it will receive the materials from the top 2 layers and or provide the sediment materials to the top 2 bed layers. So specifically, when the particles are deposited into the top 2 layers, the thickness of top 2 layers will increase. But there will be a limitation of thickness of these top 2 layers. Then if the capacity of top 2 layers are full, the materials in the top 2 layers will move to the lower layers. That is one of the deposition and consolidation process. And on the other hand, when erosion occurs, the particles in the sediment bed, sediment materials in the sediment bed will move to the water column. So when the top 2 materials in the top 2 layers are all transported to the water column, it will send the lower layers will send the materials to the upper layers, and it can transport to the water column furthermore. During the erosion process, small particles leave, but large particles tend to remain as like this. And this increases the critical shear stress of the materials in the top sediment bed layer, and we can call it as a armoring process. We can call that sediment bed is armored, and modeler can specify a constant thickness of the top layer to represent the armoring process of sediment bed. When deposition occurs during the simulation, particles in water column are transported to the sediment bed layer, and the modeler can specify a void ratio and porosity of that deposited sediment particles. And modeler can decide how we compute the consolidation of mixed cohesive and non-cohesive sediment beds during the deposition process. And these are the 3 available options for the consolidation process. So I'm going to show you how we can, I'm going to just briefly present how we can develop the original EFDC sediment transport model using EEMS GUI. So first of all, we need to have well set up of hydrodynamic simulation. And then for the sediment transport setup, we should activate the sediment transport module and specify the number of bed layers and number of sediment classes to simulate. And there are other options we need to specify. And then we are going to specify how many sediment parameter values for each sediment classes, or for each sediment class, for cohesive sediment and non-cohesive sediment for suspended load and non-cohesive sediment for bed load. because the model simulates the cohesive sediment for only suspended load, there is no option for cohesive sediment part to choose the bed load. And we can also set up the options for morphological feedback, deposition process parameters, and setups for armoring, consolidation, and resuspension calculations. And we should also specify the initial condition of sediment bed physical properties. After that, we are going to assign the boundary condition of sediment materials. As we did for the dye time series and temperature and flow time series so far, we will also assign the time series of concentrations for each sediment class to flow boundary. After all this setup, we can run the sediment transport model. So here is the GUI window for the general setup of sediment transport model simulation. Here we can choose the number of bed layers and number of cohesive sediment class and number of non-cohesive sediment class. Then here are the parameters that will be used for computing the suspended load of cohesive sediment. And we can see here, here, the reference surface erosion rate. This is the erosion rate parameter to specify the amount of eroded materials from the sediment bed. And this window shows the parameter values for 3 non-cohesive sediment classes for suspended load. So here we can choose the equilibrium concentration equation, and we can import the critical shear stress, enter the critical shear stress for each particle classes, but these numbers can also be calculated based on the embedded reference equation in GUI. You will see this process during the hands-on materials. And here is the window for the non-cohesive, tab for the non-cohesive bed load. And here is the options for morphology and consolidation process. And here we can specify the bed armoring process, and we can specify the thickness of that top layer where the armoring process occurs. And in the initial condition, we can create physical properties of sediment bed using this bed structure construction tool. And as we did so far, through the external forcing data tab, we can assign the time series for cohesive sediment and non-cohesive sediment as shown in this figure. So that is all I have for this lecture, and let's move on to the hands-on guidance. Thank you.